Nothing can go faster than light. That is the rule everyone knows. But the universe has a way of making rules feel safe, right before it shows you the trap. A beam of light can cross 300,000 kilometers in a single second. It can reach the moon almost before your brain has time to react. It can leave the sun and hit Earth in about 8 minutes. And still, somewhere far beyond our sky, light is losing. The strange part is not that light slows down, or that something blocks it, or that the laws of physics suddenly fail. The strange part is that the space ahead of it can stretch faster than the light can close the distance. That is what most people miss. Nothing is breaking the speed limit. A galaxy is not blasting through space like an impossible rocket. Einstein is not being thrown away. The universe does something colder. It keeps the law exactly as it is, then expands the road until even light cannot finish the journey. So when we say, nothing can go faster than light, the hidden ending is this. Space does not have to go faster through anything. Space is the thing getting bigger. That one idea changes the whole universe. Because if the space between two distant galaxies stretches fast enough, the distance between them can grow faster than light could ever cross it. The light is still doing everything light can do. It is moving at the ultimate speed allowed inside space. But the gap it has to cross keeps changing while the journey is happening. Imagine running toward a door at the fastest speed possible, but the hallway keeps getting longer under your feet. You are still running. You are still moving in the right direction. You are not failing in the ordinary sense. The building is simply stretching faster than your progress. That is what cosmic expansion can do to light. And once you understand that, the universe stops feeling like a place that is merely large. It starts feeling like a place that can close itself off. There are galaxies whose future light will never reach us. They may still contain stars, planets, storms, oceans, collisions, and histories we will never see. Their light can leave them perfectly, travel through space perfectly, and still never arrive here. This is not a problem of dust, weak telescopes, or patience. Those galaxies are being carried out of contact by the expansion of space itself. This is where the story becomes more than a strange fact. It becomes a warning about what the word universe actually means. The universe you see is not the whole thing. It is the part that was able to send light to you. It is the successful portion of reality. Everything else may still be real, but it may never arrive. To feel how brutal that is, start with something ordinary. Sunlight. The sun is about 8 light minutes away. That means the warm light touching your face is already 8 minutes old. You are never seeing the sun exactly as it is in this instant. You are seeing a delayed version, a message that left the surface of the sun before it reached you. If the sun could vanish right now, Earth would not know immediately. The sky would remain bright for those final minutes because the last sunlight would still be on its way. Even here, inside our own solar system, reality is not live. The moon is delayed by just over a second. Mars can be delayed by minutes. Neptune is seen as it was hours ago. The stars in the night sky are stranger still, because some of their light began traveling before the people watching it were born, before their cities existed, and in some cases before human history had even started. Looking far away means looking back in time. A telescope is not only a machine for seeing distance, it is a machine for collecting old information. At first, that sounds beautiful. Then the feeling changes, because light is not just something pretty in the sky. Light is how the universe tells you what happened. If light has not reached you, that event has not entered your observable world yet. A star can explode, and until the light from that explosion crosses the distance, the explosion has happened, but not for your sky. Your reality is limited by what has had time to arrive. Now stretch that idea to the size of the cosmos. The Big Bang was not an explosion into empty space the way people often imagine it. It was not a fireball thrown outward from one central point into a giant black room. That picture feels simple, but it is wrong in the most important way. The better idea is stranger. Space itself began expanding everywhere. Every distant observer, on the largest scales, sees faraway galaxies moving away. That does not mean everyone is at the center. It means expansion is built into space itself. There is no outer wall the galaxies are racing toward. There is no central blast site hiding somewhere beyond our instruments. The expansion is not matter flying through a pre-existing container. The container is part of what changes. That sounds almost impossible, because your brain wants a scene it can stand outside of. It wants to imagine the universe from above, like a glowing sphere swelling into a larger darkness. But there is no known outside platform where the whole expansion can be watched like that. We are inside the thing being measured. The universe is not expanding into a room. The distances inside the universe are changing. This matters because the speed of light rule applies to motion through local space. A spaceship passing you cannot move faster than light. A particle with mass cannot be pushed all the way to light speed. A message cannot outrun a beam of light in the space around you. But cosmic expansion is not a spaceship passing you. It is the distance between faraway regions increasing because the space between them is stretching. That sounds like a small distinction until you realize what it does. A galaxy very far away can recede from us faster than light, not because it is locally breaking physics, but because there is so much expanding space between us and it. Every part of that enormous distance contributes a little to the total growth of the gap. Across billions of light years, those small increases add up into something light cannot always beat. The galaxy itself is not cheating. The distance is. This is the difference that saves the science and makes the idea more disturbing. The universe does not need to violate its own laws to become unreachable. The laws already allow it. A photon can leave a faraway galaxy and head toward us at light speed. In its own local space, it is moving exactly as physics says it should. But while it travels, the space it must cross keeps expanding. In many cases, the photon still makes progress. It fights across the changing universe and eventually reaches our telescopes after billions of years. That is the light we see in deep space images. There are other cases where expansion wins. A photon can move at the fastest speed possible and still never reduce the distance enough to reach us. It is not weak or broken. It is trapped in a universe where the road grows too quickly. The speed of light is not always enough. This does not mean light is slow. It means the universe is not a fixed track. The race changes while it is being run. One way to feel this is to imagine a map printed on rubber. Two cities sit on the surface. A messenger moves from one city toward the other as fast as any messenger is allowed to move. If the rubber stretches gently, the messenger can still arrive. If the stretch becomes too aggressive across the whole map, the messenger can make perfect local progress while the destination recedes beyond reach. The messenger did not slow down. The map changed. Cosmic expansion is not exactly rubber, but the lesson is close enough to hurt. At the largest scales, distance is not just a number sitting still. Distance has a history. It can grow while light is traveling through it. When astronomers look at distant galaxies, they are not seeing live objects sitting calmly in the same present moment. They are seeing old light that survived an expanding universe. Every faint galaxy in a deep field image is a message from the past, stretched by expansion, weakened by distance, and delivered late. For some galaxies, that old message may be the only one we will ever get. We may see them as they were billions of years ago, while their present and future are already beyond contact. That is a strange kind of loss. It is not the dramatic loss of something exploding. It is quieter than that. It is separation. The universe does not need to destroy a place to remove it from your reality. It only needs to stretch space enough that the place can no longer send you light. This is why the phrase observable universe matters so much. It does not mean the whole universe. It means the region whose light has had enough time to reach us since the beginning of cosmic history. Beyond that may be more galaxies, more stars, more matter, more structure, perhaps an amount so vast that our visible universe is only a small patch of something much larger. We cannot see it directly because its light has not reached us. The more unsettling part is that the future is not guaranteed to open all of it. As expansion continues, especially because that expansion is accelerating, some regions do not become easier to see with time. They become less connected. Their light is stretched toward longer wavelengths. Their signals fade into the background. Their future becomes less available to us with every cosmic age. The sky is not only full of things that are far away, it is full of things we are losing. That is the first layer of this video. The rule is real. Nothing moves through nearby space faster than light. But space itself can stretch the distances between galaxies so aggressively that light loses the race without ever breaking its own rule. The universe keeps the speed limit, then it moves the finish line. And once you understand that, the darkness between galaxies stops looking empty. It starts looking like the place where contact fails. The easiest mistake is to think of space as empty background. We say planets are in space. We say stars are in space. We say galaxies float through space. That makes space sound passive, like a dark stage where the real objects do all the work. But space is not just a stage. It can bend. It can stretch. It can change the way distance itself behaves. This is why the universe feels so strange when you stop imagining it like a room. A room has walls. A room has a center. If something explodes inside it, pieces fly outward into the room. Our brains like that picture because it matches everyday life. Fireworks explode into air. A glass breaks across a floor. A wave spreads across water. The universe is not that simple. When cosmologists talk about expansion, they are not saying galaxies are flying through empty space from one central blast point. They are saying the large-scale distances between unbound galaxies are increasing because space itself is expanding. Nearby things do not get ripped apart by this. Your body is not expanding with the universe. Earth is not swelling. The solar system is not being stretched in any noticeable way by cosmic expansion, because gravity and electromagnetism are far stronger on these scales. Planets stay bound to stars, atoms stay held together, and galaxies or galaxy groups can keep their shape under their own gravity. Expansion becomes dominant across the immense spaces between large cosmic structures. That is why this can be happening everywhere and still not tear your room apart. The violence is not local, it is cosmic. Think of two faraway galaxy clusters separated by a vast stretch of space. The galaxies inside each cluster may remain bound by gravity, but the space between the clusters keeps increasing. The farther apart the clusters are, the more expanding space lies between them. More expanding space means more total growth in the distance. At small distances, this effect is not enough to beat light. At enormous distances, it can be. This is the part that should make the title feel less like a trick and more like a trapdoor. A galaxy does not need to fly past a beam of light. The universe can simply enlarge the gap until the beam cannot win. A car has a speed because it moves along a road. A spacecraft has a speed because it moves through local space. But if the road itself is growing, the distance between two cities can increase, even if neither city drives away. Cosmic expansion is closer to that kind of problem. The road is changing, and light, no matter how fast it is, still has to deal with the road. Now imagine one photon leaving a distant galaxy. It starts its journey long before Earth has humans, long before cities, long before telescopes. It travels across expanding space for billions of years. While it moves, the wavelength of that light stretches. Blue light can become redder. Visible light can shift into infrared. Over extreme distances and times, the expansion of the universe pulls the signal thinner and thinner. That stretching is called redshift, and it is one of the main ways astronomers know the universe is expanding. The farther many galaxies are, the more redshifted their light tends to be. Their light has been stretched by the expansion of space during its journey. In deep images, we are not just seeing faint objects. We are seeing old light that has been physically altered by the growth of the universe. That makes every distant galaxy a changed message. Not a false message, a changed one. The message arrives stretched, ancient, and delayed. This is why telescopes like Hubble and James Webb feel almost impossible. They collect light that left distant galaxies when the universe was much younger. They do not bring the present to us. They bring evidence from earlier chapters of cosmic history. A galaxy in a deep field image may look like a tiny red smear, but that smear can be a whole system of stars seen across billions of years. The image is quiet, but the fact that it exists is violent. That light crossed a universe whose space was expanding the entire time. It made it through. And here is the colder part. Not every signal gets that ending. Some light is already traveling across space and will still never become part of our sky. That is not darkness as emptiness. That is darkness as failed arrival. The observable universe is already limited by light travel time, but the future is limited by something even harsher: horizons. A horizon is not always a physical wall. Sometimes it is a boundary of what can ever be known or reached. On Earth, the horizon is where the surface curves away from your sight. You can travel and reveal what was hidden. In cosmology, some horizons are more severe. They are not just about where you are standing. They are about what light can ever do in an expanding universe. There are regions so far away that light emitted from them now will never reach us, even if we wait forever. This is called a cosmic event horizon, and this is where the universe stops feeling like a puzzle and starts feeling like a locked system. Time does not reveal everything. Waiting is not enough when space itself changes the rules of arrival. A better telescope can collect faint light. A longer exposure can reveal something dim. A new instrument can open wavelengths our eyes cannot see. But no instrument can collect a signal that never enters our future. The information is not simply faint, it is disconnected. This distinction is what makes the subject feel so big. Human curiosity usually assumes that mystery is temporary. We imagine that with stronger tools, better theories, and more time, we can push deeper and deeper until every hidden thing becomes visible. Cosmology says the universe has locked doors that are not caused by ignorance. Some doors are made of geometry. Now comes one of the most uncomfortable parts. We can see some galaxies today whose future versions are already unreachable. That sounds contradictory, but it is not. Their ancient light left long ago, when the universe was smaller and conditions allowed that light to eventually arrive here. That old light is still reaching us. But light emitted by those same galaxies today may never cross the growing distance. So a telescope can show you a galaxy's past, while its present is already gone from your future. That is the kind of idea that makes the sky feel different. You are not looking at a live universe. You are looking at old arrivals. Some of those arrivals come from places that can no longer update us. The sky becomes a museum where some exhibits are still real somewhere far away, but their next message will never reach the door. This is where the accept space idea becomes more than a clever title. Space expanding faster than light does not simply make the universe large. It makes the universe unevenly knowable. Some regions are connected by light. Some are visible only through ancient light. Some are beyond any future contact. Reality is divided by what can still send messages. That division is not obvious when you look at the night sky. Stars appear calm. Galaxies appear silent. The darkness feels like emptiness. But underneath that stillness, the universe is sorting itself into reachable and unreachable regions. The early universe may have done an even more extreme version of this. In a tiny fraction of a second after the Big Bang, according to the theory of cosmic inflation, space may have expanded at a staggering rate. This was not matter flying through space faster than light. It was space itself stretching so rapidly that regions were driven apart before light could travel between them in the usual way. Inflation is one reason scientists can explain why the universe looks so smooth on very large scales. Regions that seem far apart today may have once been close enough to share similar conditions before inflation stretched them away from each other. That idea is almost violent in its simplicity. The universe may have begun with space expanding so fast that entire regions were thrown out of contact before anything could chase them. Again, no object had to break the speed limit. Space did the terrifying part. This matters because it shows that faster-than-light expansion is not just a late universe trick. It may be part of the universe's earliest history. It may help explain why the cosmos looks the way it does today, why distant regions have similar temperatures, and why the large-scale universe seems so uniform, even across distances that ordinary communication would struggle to explain. The rule was never broken. The stage itself was moving. There is one more layer that makes this even more dramatic. The expansion of the universe is not merely continuing. On the largest scales, it appears to be accelerating. The name we give to the cause is dark energy. That name does not mean we fully understand it. It is more like a label placed over a deep problem. Observations of distant supernovae and other cosmic measurements show that expansion began accelerating billions of years ago. This acceleration changes the long-term future. Distant galaxies that are not gravitationally bound to us will drift farther away. Their light will become more redshifted. Their images will fade. Over enormous timescales, the wider universe will become harder and harder to observe from our region. This is not just a future where things are farther away. It is a future where the evidence disappears. The Milky Way and Andromeda are expected to merge one day, and our local group of galaxies remains bound together. Locally, gravity still has a future. But beyond that gravitational island, expansion keeps working. The universe becomes more isolated with age. Picture the far future. The Milky Way and Andromeda have merged into one enormous galaxy. The sky is still filled with stars from our local island, but the deep background has changed. The distant galaxies that once filled telescope images have faded toward invisibility. Their light has been stretched so much that ordinary astronomy may no longer recover them. A future astronomer builds a telescope under that sky. They search the darkness. They find stars, gas, remnants, black holes, and the history of their own merged galaxy. But the wider cosmic web that we can still map today has slipped away from view. The universe around them looks smaller than it really is. Not because the universe shrank, because the clues left. That is a savage possibility. Cosmic truth can depend on when you are alive. We happen to exist in a window where the universe is still readable. Distant galaxies still send ancient light into our instruments. The cosmic microwave background is still detectable. The expansion of the universe can still be measured. The large-scale structure can still be mapped. But this window is not permanent. As space expands, the record thins. That gives every deep space image a different feeling. It is not just beautiful, it is urgent in a cosmic sense. Every faint galaxy whose light reaches us is a survivor of distance. Every ancient signal we capture is part of a record that future time will make harder to read. The sky is not only showing us what is out there, it is showing us what has not yet been lost. This is why the title works so well. It sounds like a contradiction, but the real story is even more unsettling. The universe does not break the speed of light rule in some messy, obvious way. It respects the rule at every local point and still creates separations that light cannot cross. A broken rule would feel chaotic. This is colder because it is lawful. The universe can obey physics perfectly and still remove entire regions from one another forever. So when someone says nothing can go faster than light, the statement is true, but incomplete. Nothing can move through nearby space faster than light. Space itself can expand the distance between faraway places so much that light loses access. That is the second layer. Space is not an empty stage. It stretches the wavelengths of ancient light, changes the meaning of distance, creates horizons, and slowly turns the wider cosmos into something less reachable. Light is still the fastest messenger, but the universe decides whether the message has a road. Now we reach the part that feels like it should be impossible. If some galaxies can recede from us faster than light, why can we still see extremely distant galaxies at all? The answer is subtle, but it is one of the best parts of the story. A photon's journey through the universe is not a race across a fixed road. The road changes during the trip. The expansion rate changes. The distance between regions changes. A light beam can begin its journey in a situation that looks hopeless and still reach us later because the cosmic conditions along its path are not frozen forever. In the early universe, space was expanding, but the details of that expansion evolved over time. Some light that began far away was eventually able to enter regions where it made progress toward us. That is why saying faster than light recession means invisible forever is too simple. Cosmology is sharper than that. Some ancient light from regions that were receding very quickly can reach us. Newer light from those same regions may face a different universe, a larger gap, and a future where the route no longer works. The fate of the signal depends on when it was emitted, where it was emitted, and how the universe expands during the journey. The road is not just long. The road has a history. This is the reason the sky can show us old versions of places we can no longer meaningfully reach. It is not a contradiction. It is the result of living inside an expanding universe where visibility and contact are not the same thing. You can see a place and still be cut off from it. That sentence feels wrong in everyday life. If you can see a mountain, you can imagine walking toward it. If you can see city lights across water, you can imagine crossing the distance. Vision feels like a promise that the thing belongs to your world. In cosmology, vision is weaker than that. Seeing only proves that old light arrived. It does not prove the present version of that place can ever answer. A galaxy can appear in a telescope as a faint red object from the early universe, while its current reality lies beyond any signal we could receive. Its stars may have changed. Its planets may have formed and died. Its black holes may have grown. Its entire history after the light we see may be sealed away from us. The telescope shows a real thing, but not always a reachable thing. Now picture that as a scene. A small red galaxy sits near the edge of a deep field image. To us, it is a dim mark from the ancient universe. But in its own region, billions of years may have passed. Stars have burned through their fuel. Supernovae have torn apart old suns. Heavy elements have spread through gas clouds. New stars have formed from that wreckage. Planets may have cooled around them. Maybe nothing alive ever appeared there. Maybe something did. Either way, the version we can see is only the old message that escaped at the right time. Everything after that may be outside our future. That makes light feel almost heroic. For billions of years, it crosses a universe that is expanding under it. It carries information from stars that may no longer exist, from galaxies that may have merged, from eras that will never repeat. It arrives weakened, stretched, and delayed, but it arrives. Then you realize arrival is not guaranteed. That is the dividing line. The universe is full of light that reaches someone, somewhere. It is also full of light that will never reach us, not because it failed to shine, but because the expansion of space has removed the path. This changes the meaning of darkness. Darkness is not always emptiness. Sometimes darkness is information that cannot get here. That thought also changes the way we think about silence in the universe. When people ask why space is silent, they often mean alien civilizations. Why have we not heard them? Why do we not see clear evidence? Are they rare? Are they hiding? Are we early? Are we late? Are civilizations too fragile to last? Those questions still matter, especially inside our own galaxy, where cosmic expansion is not the explanation. The Milky Way is local enough that this faster-than-light expansion problem does not explain its silence. But on the scale of the whole universe, there is a deeper silence underneath every biological question. Some places can never talk to us. A civilization beyond our cosmic event horizon could send a perfect beam of light in our direction. The message could be clear, powerful, deliberate, and aimed exactly at us. If the expansion of space prevents that light from ever entering our observable future, then no receiver on Earth or any descendant world around our local galaxy would ever know it was sent. Not because the signal was weak, because our part of the universe was no longer on the route. That is one of the harshest limits imaginable. It means intelligence does not automatically grant access. A species can become brilliant and still be trapped inside a finite region of possible contact. The universe may contain more than any civilization can ever receive. At this point, the original rule feels different. Nothing can go faster than light. The sentence used to sound like a limit on machines. It sounded like a challenge for rockets, engines, and science fiction. But now it feels like something larger. It is a limit on connection. Light speed is the speed of causality. It protects the order of cause and effect. It prevents a normal message from arriving before it could physically be sent. It keeps the local universe from collapsing into nonsense. But cosmic expansion shows the other side of that protection. If light speed is finite and space keeps expanding, then not all places can stay in contact forever. The speed limit creates order. Expansion creates separation. Together, they make a universe that can be lawful and unreachable at the same time. This is why the phrase, "space can move faster than light," needs care. Space is not moving through another space like a spaceship. There is no outside track. There is no background room where space has a speedometer. What grows is the distance between faraway regions because the geometry of the universe changes. That is less cartoonish than the simple phrase. It is also more disturbing. A spaceship going faster than light would be dramatic. A galaxy flying illegally through space would be spectacular. But the real universe does something quieter. It expands the distance in a way that does not look like motion nearby, while still making the total separation impossible for light to overcome. The violence is hidden inside the measurement of distance itself. This is where the cosmic microwave background becomes important. It is the ancient afterglow of the early universe, a faint radiation spread across the sky. It comes from a time when the universe became transparent enough for light to travel freely. When we map it, we are seeing a baby picture of the cosmos, stretched and cooled across billions of years. That ancient glow is still here, for now. In the far future, continued expansion may stretch that radiation to wavelengths so long and energies so low that detecting it becomes far harder. A future civilization might not easily find this ancient afterglow. One of the strongest clues to the universe's beginning could become almost invisible. That is not just a scientific detail. It is a scene. Imagine a future observatory floating far from any star, built by a civilization inside the merged remains of the Milky Way and Andromeda. Its mirrors open toward the black. Its instruments listen across wavelengths for the faint background glow that once filled every direction. But the signal has thinned. The distant galaxies are gone from ordinary view. The cosmic web no longer paints the sky. The old evidence is still part of reality, but it has been stretched into a form that is almost impossible to recover. The astronomers are not stupid. They are late. Now return to the future sky. The Milky Way and Andromeda have already merged. Their spiral arms have twisted, collided, and settled into a larger galaxy. Old stars drift through new orbits. Gas clouds ignite in scattered regions. Ancient black holes sit at the center of the merged system, surrounded by generations of stars. From a planet orbiting one of those stars, a future observer looks up. The local sky may still be rich. There may be stars everywhere. There may be nebulae, clusters, white dwarfs, neutron stars, and black holes. But the deep universe beyond the local group has faded. The galaxies that once filled our most powerful images are no longer bright islands in the background. Their light has stretched, dimmed, and slipped out of reach. The cosmic web that once revealed the large-scale structure of reality has become a ghost story written in wavelengths too thin to recover. The future observer may build enormous telescopes. They may search longer than we ever could. But the sky available to them is poorer than ours. Not because they are less intelligent, because they arrived late. That visual matters. A future civilization standing under a darker cosmic background may not easily discover what we know now. They may not see the same evidence of expansion. They may not detect the same ancient afterglow. They may not look out and find the same distant universe staring back. The truth has not changed. The access has. That is why our own moment is strange. We are not at the beginning of the universe, and we are not at the end. We live in a time when ancient light still reaches us, when distant galaxies still mark the depth of cosmic history, when the expanding universe still leaves enough evidence to read its past. We are not seeing everything, but we are seeing enough to know that there is more than we can ever reach. That is a strange privilege and a strange threat, because the more we understand the universe, the more we realize that knowledge is not only a matter of intelligence, it is also a matter of access. You cannot study light that never arrives. You cannot answer a signal that never enters your horizon. You cannot explore a region that space-time itself removes from your possible future. The universe is not required to make itself available. That line is uncomfortable because it goes against the way we want discovery to work. We imagine reality as something waiting to be uncovered, hidden, difficult, distant, but ultimately open. Cosmology says some of reality may be closed to us forever, not by secrecy, but by structure. Over enough time, space keeps expanding while light keeps traveling, and horizons begin to form. The map of what can be known becomes smaller than the map of what exists. So the title is not just a paradox, it is a trapdoor. Nothing can go faster than light, and that remains true in the deepest local sense. But space can stretch the distance between faraway places until the fastest thing in the universe is no longer fast enough. Even a perfect beam of light can fail if the universe removes the path. A message can be sent with no mistake at all and still never enter our sky. A galaxy can remain completely real while leaving our future forever. That is how the universe wins without cheating. It does not break the speed limit. It changes the distance. And somewhere beyond the edge of what will ever reach us, stars may still be burning. Worlds may still be turning. Entire histories may be unfolding in the dark. They are not waiting for us to invent a better telescope. They are not hidden behind a curtain we can someday pull aside. They are beyond the part of reality that can send us light. So when you hear that nothing can go faster than light, remember the colder truth behind it. Light is the fastest thing inside space, but space decides how far light has to go. And if space stretches the road enough, even light never comes home.